Well, 1 week from today, so 14th. So two things, 14th and that was also the same day as midterm. Okay? Good book right there. Make sure you look at it. Okay. Oh, you'll be fine. How many of you guys are taking the ACT this year? 1, 2, 3. Okay. All right.
Yeah.
What? Do they have any classes to prep you for that at all, or?
It's called like a college
What's that?
prep.
Well, I was wondering if, like, do they offer like an ACT prep course?
Oh no.
I have a question for you guys, because I used to do this years ago when I first started teaching here. This was probably about 12, 13 years ago. I offered an ACT prep course twice a morning from 7:30 to 8. How many of you guys would think about doing that if there was like an ACT prep course for math that met in the mornings? How many of you guys would think about taking that? 7:30 to 8. It would just be a half-hour thing, twice for a trimester, twice a week for a try.
If it wasn't on Wednesdays.
When are you guys planning on taking that? How many of you still need to take it right now? Okay. When's the next date coming up to take it? When are you taking yours?
Well, since I will have Trigan before the school one, and it's also on prom, I'm gonna take it June 8th, so it's like 1 week ago.
That's when I'm taking mine.
Because the one that the school's hosting is April 13th, which is also the same day as prom.
How many of you guys would have interest in a course that met in the mornings? Really?
Yeah.
Okay. I'll do some digging on that, some talking, and see. I might implement that again. All right. Well, we'll talk about that at another time or another day, but what we'll start here with today, kids, is this. Guys, you've noticed the poster up here in the past. It says surprise, the letter E is also a what? It's a number, okay? And what the letter E is known as in 5.1 is the natural base, okay? So the essential question pretty much today is going to start exploring that. What is the natural base E? Okay, so our goals today is to first of all define and use the natural base of E. We're going to look at what the graph looks like here, and then we're also going to solve some real life problems involving this. Now this section won't take very long, okay? This won't take very long to get through, and you'll have some time to start on the online, but some vocabulary we need to understand is up there. My first vocab word is the natural base E. So how about a volunteer to read that definition for me?
The history of mathematics is marked by the discovery of special numbers such as pi and I. Another special number is denoted by the letter E. The number is called the natural base E. The expression 1 plus 1 over x
To the x power, yep.
Approaches E as x.
Okay. How many of you guys have a calculator right now? Okay, here's what I'm going to tell you right now. All right, what this is like, it's coming from 1 plus 1 over x to the x power. So it's like saying 1 plus 1 half, or 1 plus 1 third, or 1 plus 1 fourth, or 1 plus 1 fifth, or 1 plus 1 sixth. And we continued. This x stays the same, so x is always going to get bigger and bigger and bigger and bigger, okay? Now the thing I want to tell you about natural base of E, we define it as this value, 1 plus 1 over x right here. Sometimes it's going to be written as 1 plus 1 over n to the n power as well. So if you see it this way or this way, just understand the n and the x are like the same value, okay? So here's what we're going to do. I'm going to look at just some values right here. What I want someone to do is to we're going to punch in 3 values. Okay, I need 3 volunteers with calculators to help me. Maddie's one. Somebody else with a calculator help me. Belle, Jazzy, you guys help me with this, okay? You ready for this? Okay. Pick an x value. I don't care. Positively. How much? 2? You're picking 2? Okay. So I want you to type in 1 plus 1 half in your calculator in parentheses and then raise that value to the second power, okay? Jasmine. You have to pick something in the hundreds, somewhere between 100 and 999. 150 or 115?
150.
Okay, Jasmine's going to do 1 plus 1 over 150 to which power, kids? Okay. Bell, you get to pick something bigger than 1,000.
2001.
I like it. 2001. So Bell, what you're going to type in your calculator is 1 plus 1 over 2001. So what power, kiddo? Okay. When you have your values, tell me what you get. Maddie, do you have yours yet?
I got 2 and 1/4.
2 1/4 about, so about 2.25.
Yeah.
Okay. Jasmine, you have your value yet?
Yeah, I have 2.71.
2.71 after the 1.
It's
Say it again.
2.709.
709, 2.709. So obviously this is increasing a little bit, going from 2 to 150, it's increasing a little bit. So if it keeps increasing, what do you think the value of 1 plus 1 over 2001 to the 2001 power is going to do? Probably going to be in the 3s, right? What'd you get there, Belle?
I got 2.7.
2.718, hopefully?
Yeah.
Somewhere around there? Okay. Take a look at this right here, kids. Who wants to do 1 million for you down there? 1 plus 1 over 1 million to the 1 millionth power. Whoever you're good at punching big numbers in there, do that. Change your 2001s in there on your entry. Change it to 1 million. So type in 1 plus 1 over 1 million.
How much is the top? Is it
2.25, I'm sorry, yeah, it's kind of small up there. 2.25 is the first one. And what I'm getting at here is this. Val, when you got that 1 million typed in for X in both places, tell me where you end at. Six zero. 2.718 again. Nope, you're right. Okay. Anybody want to guess what would happen as I continue to get bigger and bigger and bigger with numbers? Well, they kind of tell you. Can you guys see this chart up here? Okay. When we put these numbers in right here, here's the 1 million. Did you get 2.718 like this right here? Okay. Next one they're going to go to 10 million. And then what value do they get out again, kids? 2.718. This number kind of stalls out at 2.718. So if I would put a trillion in there, Val, you want to put a trillion in or take my word for it? Yeah, if you put a trillion in there, it's going to get really close to 2.718. So what we say here, guys, is the natural base of E is found by doing this as n gets really big right here. And that value that approaches it right here, you want to write this in. The value of E is about 2.718, okay? Now, guys, that number is irrational. It goes on forever. It goes on forever. Doesn't repeat and it goes on forever. It's irrational. What's probably the most famous irrational number you know all the time? Which is approximately what? 3.14159, blah, 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 right? We call it 3.14. The thing I want you to put in your brain here is this. E is also a famous irrational number, okay? And E is about 2.718. How many of you guys have heard your parents talk about banking in the past and money? Any of your parents ever talk about interest earned on something? Okay. This is kind of like continually interest, compounding interest, okay? Continually compounding interest. It's like saying, well, what if my interest was 1/1,000,000% and I compounded it 1,000,000 times? What am I getting out for a yield? Well, it's about 2.718 times. This is where this number's coming from, okay? And we're not going to get too technical with it, but I want you to understand, first of all, where does it come from? It comes from 1 plus 1 over n to the nth power, and these n values continue to do what, kids? Get bigger and bigger and bigger. And as I get these numbers being bigger and bigger and bigger, this number eventually stalls out at what value? 2.718. Now we know what irrational numbers. Irrational numbers are any real number that cannot be written as a simple fraction, so E is one of those values. Okay? Things to remember then to be successful in this section are properties of exponents. Let's just read through this. It says when you raise a quotient to a power, you raise both the numerator and the what? So just to make sure we understand this, if I have A over B to the nth power, there's my quotient. This is the same as what, kids? A to the n over B to the n. So remember that rule. That's going to come in handy today. It also says when you raise a number to what? 0 power, you're going to get what? That's going to be important. Negative exponents are the reciprocals of the... So if I have a to the negative n, this is the same as 1 over a to the positive n power. And make sure you understand those rules, okay? You guys are going to hear me talk about exponential growth functions. These are going to be growth whose rate becomes ever more rapid in proportion to the growing total number or size. Exponential functions that grow typically look like this, graphically. Okay, and I'll show you some examples here. Exponential decay functions are going to be graphs that start out high. They decrease, but they eventually flatten out. Okay? And then the next term, that's going to carry over to the next page, is called asymptote. Okay? Have you ever heard of the word asymptote? Okay, an asymptote is this. It's a line that continually approaches a given curve but does not meet at any finite distance. So what it's saying is this. You might have a graph. I'm going to put this right up here. Okay, you might have a graph that looks like this. I'm going to draw a horizontal dotted line for E. Okay, I'm going to draw a horizontal dotted line up here for E. I'll slide that up here a little bit. E is what value again, kids? Okay. Let's say that this is E right up here. The graph of this right here, the graph right here for this is going to start out at, well, if I start out at 1, it kind of goes like this right here. Okay. The graph for my function 1 plus 1 over n to the nth power, kids, kind of looks like this a little bit. When I was putting really big numbers in here, or like when Bell put 2001 in there, or we put 1,000,000 in there, that got really close to what value? 2.718. And as I get closer and closer and closer, the further I move right, this line is getting, the red line is getting closer and closer and closer to the dotted line, but is it ever going to cross that line? Never will. Okay? Zeno's paradox. You guys know Zeno's paradox at all? I'm going to start at this wall right here, and I'm going to go to that wall. But the rules are this. I can only go halfway and stop. And when I stop, I can only go halfway to the wall again. So it's kind of like saying, okay, I start here at the wall, and I walk halfway to that wall. Now I've stopped. Okay, now I can only go what? Halfway. And there's halfway, now I stop. And now from this stopping point to the wall, I can only go what? Am I ever going to get there if I keep going halfway each distance when I stop? Now go what, kids? Halfway. Now what? Halfway. Now what?
Keep going.
You want me to do this until I get there?
Yeah.
Wait a minute. I see what you're trying to do. You think if I keep going halfway that you'll never have to do homework again, right?
Yeah.
Is that what you're telling me?
Yeah.
Will I ever get there if I keep going halfway?
No.
And what that wall is that wall, if I apply Zeno's paradox right here and keep going halfway the previous distance, I'll never ever get there. And that's kind of what this asymptote is. It's saying, okay, here's your graph, but this graph right here is never going to cross that line. It'll keep getting closer and closer and closer to it, but it will never get there. Okay? That's what an asymptote is. All right. Okay, percent increase, percent decrease. We'll talk about that more. You can read that. It's the amount of quantity increases per 100 units. Compound interest. This is going to be interesting. This is going to be a great real-life application for you today. But compound interest is. How about a volunteer to read that definition? Who wants? Go, Jazzy.
Compound interest is the addition of interest to the principal sum of a loan or deposit, or in other words, interest on interest. It is a result of reinvesting interest rather than paying it out, so that interest in the next period is then earned on the principal sum plus previously accumulated interest.
That sounds like a tough definition. Okay? How many of you guys like money? How many are like me and don't have a lot of money? Okay? How many want to make a lot of money? Okay. And when I say make money, you're going to earn it, right?
Yeah.
Okay. Interest on interest. Do this for me. Let's start with $100, okay? And let's say I'm going to let you earn 6% interest in a bank every single day. 6% interest every single day, okay? So do this. Who has a calculator for me? Punch 100 in your calculator. How many people would take 6% interest every single day?
What's the other option?
I would, because most of it's like semi-annually or annually the whole year, okay? I'm going to tell you you're starting out with $100, and if you could earn 6% on that every single day, just by investing it, here's what would happen, okay? Take 100 times 1.06 and hit enter. Where are you at? So in one day, you've gone from $100 to what? 106. But now this time, when I turn around and take 6% of my balance, we're not taking 6% of the original 100. We're taking 6% of what now? 106. We're adding, we're doing interest on interest earned already. That's what compound interest is. So take 106 times 1.06 again for day 2. 112 point, ooh, we earned a little more. Now take that 112.36 times 1.06 again. Okay? Let's just give you an example right here. Don't write this down, but what I'm doing here, guys, is this. I said start out with how much money. And we're timesing this by how much each time? How many times do you multiply by 1.06? 3 times. That's like taking 1.06 to which power? Well, what if I told you this? What if there was a company out there saying, throw me $100 and I'll give you 6% compound interest every day? Well, how many days are in here? Anybody want to guess what $100 would be worth if you added 6% to it every single day at compound interest? Well, how many days are there in a year? Do this for me in your calculator. Go 100 parenthesis 1.06 and raise that to the 365th power. All right, so what that means is that is worth 172. Wow, let me type that in. 100 times 1.06 to the 365th power. Is that right? You have 1.724411 to the 11th power times 10 to the 11th. Is that right? So I'd have to think about that. It would be 9 zeros. You would be worth $172 billion if that was true in 1 year. Your $100 would be worth $172 billion. Now, is all interest going to be that good? Absolutely not. But do you see how things can blow up quickly when you keep compounding interest on interest earned already? That makes sense? Do this for me. Imagine you're only getting $6 each time. Take 6 times 365 for me. Take 6 times 365. You got that number? Got that? Now divide by 100. I just think this for me, kids. Take 106 times, no, do this. Do 6 times 365 again. You got that number? Now add 100. It should be like 2,000 and some. If you were doing just 6% interest on your original $100, not the interest you earned, you would only have like $2,290. But doing interest on the interest you've earned and compounding that over and over and over, you were at like $17 billion or $172 billion. Is simple interest better or compound interest better for you? And that's where that number is coming from. It's going to talk about compound interest, okay? You're going to see a function for compound interest written as follows. Let's see what terms they use, R and T. This is a formula you're going to need to know for compound interest. What letter, or I'm sorry, which number shows up in that formula?
E.
E does, okay? It's going to talk about continuously compounding interest, okay? All right, there's a lot of terms in here that are going to be very new for you. I don't doubt that for a second. And we're going to work our way through them as we go through the examples. But you got to understand that this number is going to make things blow up quickly. E is about what value again?
2.17.
Okay, simplifying natural base expressions here, kids. Rules of exponents are all going to apply. If I go e to the second times e to the ninth, anybody have a guess what that would be? E to the 11th. How many e's are you multiplying here? In the first part. How many e's are you multiplying here? So how many e's together? Okay. Don't write 2.718 to the 11th. Just leave e as that number. It's the same thing as saying this, kids. It's the same thing as saying, well, this is like 3 squared times 3 to the 9th, which would be 3 to the what, kids? 3 to the 11th, okay? Take a look at this one. How about the 25 over 5 part? What's that going to simplify to? 5. What do you think you're going to do with 13 and 12 when it's written like that? So 5e to the first, or just call it 5e, okay? This is all stuff you've done, but instead of having an x up there, what value are you working with now as your base? E, okay? Help me with the next one. I have 2e to the negative 3x. I've got to take 2 to what power first, kids? So this is the same as 2 to the 5th. What exponent's already with the e here, kids? Negative. But I got to bring that 5 into this, which would make this e to the negative 15x, right? Okay, quick question. Can you evaluate 2 to the 5th?
Yeah.
So this would be the same in simplest form as 32 e to the what, kids? Now I have a question for you. Do we like writing stuff with negative exponents? And if you want to get rid of a negative exponent, you can take part of the base with the negative exponent and move it to the opposite side of a fraction bar, and it turns to a positive. So if there was a fraction bar right down here, I could leave the 32 up top, because this negative 15x is only associated with e. It's not saying take this, because 32 came from 2 to the 5th. This is the same then as 32 over what, kids? E to the... Okay, and that's what you would have right there, okay? So those are all rules that we've talked about in the past, kids. All rules that we've talked about in the past. You're going to get asked to say, I want you to simplify these, okay? You're going to see a lot of stuff like that. You'll get used to that as you progress through the assignment that I'm going to give you today. Okay? All right. Big core concept. We'll look at some examples on the next page. We're almost done. Core concept, natural base functions. A function of the form y equals a. A is some number times e to the rx is called a natural base exponential function. Hear me out. When a is greater than 0 and what? R is greater than 0, the function is an exponential growth. So if a and r are bigger than 0, in other words, what kind of numbers? Okay, I'm going to say a is positive, R is positive, what kind of function do you have? And I'm going to move that up here, I'm sorry. A is positive, and R is positive, what kind of function do you have? Growth. And growth functions are typically going to look like this. Okay? Sometimes you might see them look like this, but either way, moving from left to right, is the graph increasing or decreasing? Okay? When A is greater than 0, but R is what? Less than 0, so the function is going to be what? In other words, A is going to be a positive number, but R is going to be what kind of number, kids? R less than 0? Okay, and this is what a graph is typically going to look like here for these. Okay, could look like these. Primarily the first one, though, okay? Well, let's put this into action, okay? The thing you really need to understand is if R is a positive value, what kind of function do you have? If R is a negative value, what kind of function do you have? Okay, so here's our function. Y equals A times E to the Rx. Let's go to the next page and put this in play.
Does it ever matter like A is a negative? Or will A never be?
In this section, it's going to be positive. And yes, it will matter. Okay, and we'll talk about that as we get through the chapter, okay? All right, so here's the deal, kids. It says graphing natural base functions. Okay, natural base functions take on the form y equals some value a is some number, times e times r to the x power. Okay? It says tell whether each function represents exponential growth or exponential decay. Graph the function. We'll do some graphing from Desmos. I think that that's a good way to see this. Okay, talk to me, kids. In letter A, f of x equals 2.5 e to the x. Specifically, how many x up there? So it's 2.5 times e to the 1x. Okay, help me out, kids. That 2.5, that's the a value. Is that positive or is it negative? That's positive. That's good. How about your r value? What is r? 1. Okay? I have to tell you something about A. Okay? A is like a starting value. Because think about it. I said anything to the 0 power was going to equal what? 1. So starting is like saying we start when x is equal to 0. Think about this, kids. What would e to the 0 power be if I threw that in here? 1. And then 1 times 2.5 is still what? So this a value out front is always like your starting value or an initial amount. So if I start talking about, say, hey kids, what's the initial amount? You're going to tell me, Parson, we're starting with 2.5. And then we're going to blow it up by the natural base e to the 1x power, depending on what x is. Okay? Is this going to be growth or decay, kids? Growth, because a is positive. And what else? R is positive. So let's check it out in Desmos and see. Okay, this is going to be growth because A is positive and R is positive. So let's check it out and see. So if I run Desmos here, oh, Desmos, where are you? I love Desmos. Projector mode. What function am I typing in there? F of x equals what? Okay, and I can type it in as y equals instead of f of x. 2.5, whoops, I don't think that's a decimal, is it? Yeah, it is. Oh my gosh, where's the letter E at? Go to ABC like this, type in E, 2.5 E, and then we're going to raise it to what power, kids? 1x, or just x. You tell me, growth or decay? By the way, your your y-intercept right here. To start with, when time x is equal to 0 or x is equal to 0 to start with, what value are you at? Isn't 2.5 like the starting value right here on the y-axis? That start value is also like the y-intercept. Okay? So if I go back here, by the way, does this function show growth as I move left to right? Is it showing growth as I move left to right? Yeah. Okay. By the way, what's happening right here? It flattens out. It's going to flatten out forever. What do you think the x-axis is going to be called for this function? The x-axis is an asymptote. There's a horizontal asymptote here at 0. Okay. All right, so it's growth. I'm going to make another note about A. A is like the y-intercept in this. Okay. Hey! Y equals e to the negative 0.2x. Growth or decay? Why decay? Someone say it again. R value is negative. Okay, what's the A value by this? A is 1, R equals negative 0.2. This indicates decay. Let's just check it. Y equals e to the, was it negative 0.2x? What's the starting value in this function? Ah! Shock. Was it negative 0.2? Starts out here. What's it doing, kids? Going flat. Where's it flattening out? What towards what value? Okay. What did we say the starting value was going to be? If R is positive, you have what? If R is positive, you're going to have growth. If R is negative, you're going to have. Okay. Got it? Give me some sort of sign that you're alive right now.
Yeah.
Got it? Okay. Well, then, let's talk about this compound interest thing because we've kind of touched on it a little bit. If I do simple interest on $100 at 6% a day, that's only worth like $2,200. But if I do compound interest at 6% a day on $100, that's worth like $172 billion. You taking the simple interest or compound interest if a bank's offering that? Take the compound interest. When you guys grow up in life and they say, how do you want that interest accumulated or accrued to you? You are going to say, I want compound interest because for you, that's better with what? Money. And that's the one thing in the world that we all kind of agree on that we like. Okay? Sam can say she likes the Denver Broncos, and I can say I like the Minnesota Vikings. We don't necessarily agree on that, but I do agree that we like to have money, right? The more, the better. Which interest am I telling you to take as kids? Take the compound interest, okay? Example 3, modeling with mathematics. First of all, the concept we need to understand is this. When interest is compounded, how? Continuously. That's where that E comes into play. The amount A is in an account after what? P is given by the formula A equals P times E to the what? Now guys, this number in front of E is like, it says P, right? But we said the number in front of E is like the amount you start with. Okay, P is the principal. So principal means how much are you starting with, okay? This is not Mr. Caton. We are not compounding Mr. Caton today. All right? This is the amount you start with. And R is going to be the what? But this is the biggie. That R is expressed as a what, kids? Okay. Modeling with mathematics. Here we go. Volunteer to read example 3, please. Sam, you got it?
You and your friend each have accounts that earn annual interest compounded continuously. Use the graph in example 3 for the balance of your friend's account over time. The balance A in dollars of your account after T years can be modeled by A equals 3,900 e to the 0.05 t. Which account has a greater principal? Which account has a greater balance after 14 years?
Okay, so I'm going to pull example 3 for you here in Big Idea. So let me look at this right here quickly. What time frame are we talking about, kids? How many years?
14.
14 years, right? And what we're after here, kids, what we're after here in example 3, take a look at example 3. Where? Here we go. Example 3 is right here, okay? I'm going to blow this up so we can see this a little bit. Okay, first of all, in 14 years right here, this is a balance that the kid has. First of all, their function is written right up here as A equals 4,500 e to the what? 0.04 t. So this person right here in this graph right here with an exponential, what's their principal amount? How much money did they start out investing? 4,500, and that's only growing at what percent? What's the percent rate up here? 4%, okay? So here's this right here. At 14 years is right about in the middle here. They're pretty close to about, they're just a little over $9,000 here, okay? They're just a little over $9,000. But I'm going to write that other function down, okay? So here's what I have. The other function for our friend is A equals 4,500 e to the 0.04 t. So the question becomes this. Which account has the greater principal? What was my principal right here, or our principal in this example? Okay, $3,900, wasn't it? What was your friend's principal, kids? Your friend's principal or starting amount was how much? Okay, so it says which has a greater principal? Who's going to have more principal? Your friend has more principal. And here's the reason. Because, is it okay to say 4,500 is more than 3,900? Okay, so that's the first part. Your friend has more principal because he has $4,500 to invest. Okay, my question then is this. Who's getting a better rate? What rate is your friend getting? 4%. What rate are you getting? So when you go in and you want to invest money, do you want your percent to be higher or lower? Higher. Now when you're buying stuff and they start charging you interest to pay back, do you want that interest to be higher or lower? Okay, so it says which account has a greater balance after 14 years. So I have a question. I need a couple volunteers to run some calculator numbers for me. Okay, who's willing to put 14 into the friends function? 4,500. Oh, you guys might want to figure out where E is at in your calculator, huh? Okay. How many of you guys have the calculator kind of like Maddie? Hold that up, Maddie. Okay. Define E in that right here. Type in 4,500. Oh boy. Do you find E? Where's that at? Okay, so some of you guys have to hit like the second button and then the LN. You might have an LN button. Okay. Type in 0.04 for your exponent. Well, we're going to evaluate this after how many years, kids? 14 years. So type in 0.04 times 14 up there as your exponent. Is there anybody that hasn't found an E button in their calculator? Anybody needs help finding E in their calculator? Okay, when you plug in 14 right here for your friend's balance, after 14 years, how much does your friend have?
7,878.02.
7,000.
878.02.
Okay. Now, for us right here, kids, we're going to type in 3,900 times e to the 0.05 times, what's the t-value we're plugging in again for a number of years?
14.
Okay, type in 3,900. I want to check something. Do I have an E button at all, kids? Okay, I agree. How about when you punch it in for your 3,900 e to the 0.05 times 14? What do you guys get there?
7,853.60.
So who has more money? Your friend, but what's happening to the gap? Getting smaller and smaller and smaller. Eventually, over time, who's going to be making more money? You will be. Okay. So keep that in mind, kids. I'm going to send out the outline over this, but keep in mind, E is somewhat. We're going to talk exponential growth and exponential decay with this. I think you'll do okay with this. All right.